Okay, so in today's video we want to look at the two things that we skipped over in the last video, which was essentially looking at differentiating x to the n where n is -1. Okay, and similarly antidifferentiating ax plus b to the n where n is -1. Okay, so 1 on x and 1 on ax plus b. So to do that we want to think about some derivatives first of all. So when we differentiate log e of x, you might recall, I hope you recall, that we get 1 on x. However, we also know that when we differentiate log e of ax, we also get 1 on x. And we can think about that in a couple of different ways. Okay, we can think about the fact that what's actually happening here is that when we differentiate log e of ax, we can think about it as a chain rule. So it's derivative of log e of something is 1 on something, and then we multiply by the derivative of the inside, which is a, and so in the end we get 1 on x. The other way we can think about it is that this is actually, thinking about our log laws, this is log e of x plus log e of a. And we know that when we differentiate log e of x, we get 1 on x. Log e of a is just a number. When we differentiate that, we get 0. Okay, so whether it's thinking it as a chain rule, thinking it through as a chain rule problem, or thinking it through by splitting up your logs and then differentiating, regardless, if we have log e of a number times x, we still also get 1 on x. So this again potentially presents a problem, because we're trying to think about what's the antiderivative of 1 on x. Okay. And so the question is, well, is it log e of x, or is it log e of a number times x? Okay. And the thing is that, well, technically it doesn't really matter, but this would be greatly overcomplicating things. So remember, what we have to remember is when we, let me write that on another line, or is it log e of ax? Okay. So this would be really complicating things to write it this in the second way, because remember what we also need to add when we antidifferentiate is our plus c. Now if we gave our answer as this, let's again think about that. Well, that's log e of x plus log e of a plus c. Now log e of a is just a constant value, so all of that is just a constant. So it is just going to be log e of x plus c. So whether it's so if we're antidifferentiating 1 on x, it'll always just be log e of x plus c. C might well involve log, and we might be able to combine them back together to write it as log e of ax, or it might not, or we might not have any information to work out c. But the point is that if there is a number here, or if there's a way to write it with a number there, that will be part of the c value, okay, and we'll be able to calculate that if we're given a key point. Okay, so when we're antidifferentiating 1 on x, or x to the -1, it is always just going to be log e of x plus c. Okay, and obviously this whole thing is depending on the fact that x cannot be equal to 0. In fact, right now it's actually depending on the fact that x is bigger than 0, and I'll talk to that a little bit further down, but let's just write that there for now. Okay, let's think about differentiating a slightly more complex version of log. So when we differentiate log e of ax plus b, we use the chain rule, okay, and we would get 1 on ax plus b, and then we would need to multiply by the derivative of the inside, which is a. So we would get a on ax plus b. What I want us to think about, I'm going to start to formalize this process of reversing what we learn about our derivative. Okay, so if we learn that the derivative of this thing gives us this thing, we automatically, in knowing that, learn something about an antiderivative. So that derivative statement implies that if the derivative of the green thing is the purple thing, that means that the antiderivative of the purple thing has to be the green thing. Okay, plus c, we'll add that on at the end. So we're not interested in a rule for antidifferentiating a on ax plus b. We want to know about 1 on ax plus b. So let's think about how we could manipulate this derivative. Okay, a is just a constant value. It's a constant times a function. So we know from our integral rules that we can just take that a out. That's the same as a times the integral of 1 on ax plus b. It's just a constant value. And therefore, if we want to know what the integral of 1 on ax plus b is with respect to x, we can just divide both sides by a, and we know it's going to be 1 over a times log e of ax plus b. And then obviously plus c. Okay, so starting with what we learned from the derivative tells us if we differentiate the green thing, we get the purple thing. Immediately from that, we know that if we anti-differentiate the purple thing, we get the green thing. From that statement, which is this first line here, we then look at, okay, how can I manipulate it to show me the antiderivative that I actually want? And the only thing that's different here is that we're just multiplying by a. A is a constant value. We know properties of integrals. We can take that constant value out of the integral, and therefore then we can divide it over to the other side. And we find that the antiderivative of 1 on ax plus b, or ax plus b to the negative 1, is 1 on a times log e of ax plus b plus c. And that will be only true if x is bigger than negative b on a. Okay, it's a similar restriction to the one I added in up here. It's an important one. I'll talk a little bit more about that. Again, what we've done here is essentially undone the chain rule. We can only come up with a formulaic rule for that if the inside function is a linear function. So if this was log e of x squared, we couldn't think through this process in the same way. We would need more complicated techniques which are beyond the scope of what we're going to cover. Okay, so for example, let's anti-differentiate each of these. So we've got antiderivative of 3 on x, where x is bigger than 0. Okay, so as long as the denominator is bigger than 0, there's a restriction that says that the denominator is bigger than 0, we can use the rules we've just talked about. Okay, and so we know that this is just the same as 3 times the antiderivative of 1 on x. Okay, and so therefore it is 3 times log e of x plus c. Okay, all of which is only true when x is bigger than 0. And that's because the log function is only defined when x is bigger than 0. Okay. If we're anti-differentiating 1 on 5x with respect to x, there's two different ways that we could do this, and they're both correct answers. And this is where I want you to be a bit careful. So we could think about this as following this rule up here. Okay, that this is 1 on ax plus b, where a is 5 and b is 0, obviously. And so if we follow that rule, we get 1 on 5 times log e of 5x plus c. Okay, and that's perfectly correct. Or we could think about this integral as being the same as 1/5 times the integral of 1 on x, in which case it is 1/5 times log e of x plus c. Now for this question, both of these answers are correct answers. If we then had information about, for example, when x equals 1, y equals something, we could then find the value of c, and we would get different values of c. Okay, this second one would involve log e of, this second one would involve log e of 5 somewhere, so that it would actually combine together with the log e of x back to give you log e of 5x. Okay, but for this question here, where it's an indefinite integral, both of these answers are correct answers to this question. I would strongly encourage you to try and make this your preference, okay, because this will often ultimately result in a simpler calculation for finding c further down the track, and a simpler simplification. Simpler simplification is not necessarily the best way, but either way you'll get to the same answers. Okay, but for this particular moment, both of those are perfectly correct answers, and technically the same, given that we have an unknown constant value. Okay, part C. We're finding the antiderivative of this function. We've got this restriction that makes sure that the denominator is bigger than 0, and that's important because we're going to have log of that, and we know that the domain of log, the thing inside the log, has to be bigger than 0. Okay, so we're anti-differentiating 1 on ax plus b essentially, and we know we get 1 on a, which in this case is 1 on 7, times log e of ax plus b, so 7x minus 3. Again, only going to be true if x is bigger than 3 on 7, okay, and that's because otherwise we'd have problems with the log. part D, it's the same thing, except we've got that constant value of 4 on the top, so we can sort of just think about that as being out there. You can also think about it as being minus x plus 3, so your a value is -1, if that's helpful. I personally don't like to write it like that, but helpful to think that through in your head if you need to. And then we're going to have 4 times antiderivative of 1 on 3 minus x, so that's going to be 1 on -1, that's your a value, times log e of 3 minus x plus c. So we're just going to have -4 times log e of 3 minus x plus c. Again, there's potentially some slightly different ways that we could have written that, because what we could have done at the beginning was to actually take -4 out of that integral, and then it would have become 1 on x minus 3. And so then our answer we got would have been -4 times log e of x minus 3 rather than 3 minus x. Again, that'll all come out in the wash once you calculate your c value. You get a slightly different c value depending on how you've written this part of your antiderivative. Okay, we'll see that come to the fore a bit later on. Okay, so applying those two rules. Once again, this rule here will tend to be a rule that you forget how to execute, but it does tend to be more the 1 on ax plus b to the power of n that's a problem. Okay, so then we get some slightly more complicated examples, and again we must remember that there is no such thing as product rule and no such thing as quotient rule when we are integrating, so therefore we must work out how to simplify the expression before we can integrate it. So this one here, we want to be able to simplify this so we don't have division of two functions. We've got a quadratic divided by x at the moment, so we want to simplify that. So let's expand out that quadratic. Again, we haven't anti-differentiated, so it's still equal to the antiderivative. That'll be x squared plus 4x plus 4 when we expand out that perfect square on the numerator, and we have all of that over x. And now if we simplify this fraction by dividing each term by x, x squared on x is x, 4x on x is 4, and 4 on x is 4 on x. Now we can anti-differentiate each of those things. The antiderivative of x, remembering x is x to the 1, so add 1 to the power, divide by the new power. Antiderivative of 4 becomes 4x. Antiderivative of 4 over x is 4 times 1 on x, so it's 4 times log e of x plus c. Again, we've got that restriction that makes sure that we're not going to have an issue with the definition of our answer, with the domain of our answer. Okay, again, let's have a think about this one. So we've got x on x minus 4 essentially. Okay, so anti-differentiating x on x minus 4. Okay, so this can't be split up in the same way as we can split up a fraction when we just have a single term denominator. Okay, this does not equal x on x minus x on 4. Okay, so please be careful about that. We can use a technique that we've used in other problems before now, okay, which is if I want to simplify this so that I don't have x's in the numerator, I want to be able to, essentially, I sort of refer to it as forcing the denominator into the numerator. So I'm going to think about, I need there to be an x minus 4 up here, so I'm going to be able to do some cancelling down. So I just write it up there, and then I work out what else has to go up here in order to still keep these two things actually equal to each other. So if I put a plus 4 there, they're still actually equal. And now what I can do is split this into two separate fractions. It's now x minus 4 over x minus 4 plus 4 over x minus 4. X minus 4 over x minus 4 is just 1. So we've got 1 plus 4 over x minus 4 dx. Antiderivative of 1 is x. This is 4 times 1 on x minus 4, so we're going to have 4 times log e of x minus 4. We technically need to divide by a, but a is 1, okay, so in this case it's not going to make any difference. Plus c. Oops, sorry. And so there's our answer. Let's try one more of those where we need to do that sort of forcing the denominator into the numerator technique in order to simplify the fraction to a point that we can anti-differentiate. So haven't anti-differentiated yet. We're working on simplifying the fraction. In order to be able to cancel the x's out of the numerator, I'm going to need like terms so that I can cancel. So I want there to be x minus 1's in the numerator, and I can then focus on breaking up and cancelling down this fraction. So then let's work out what needs to go around that. So on the numerator up here, there's a 2x. So there has to be a 2 outside that bracket, so I get a 2x. Then when I expand out that bracket, that would give me 2x minus 2, but I need there to be plus 3. So there's going to need to be a plus 5 there to make that work. If you expand out that numerator, that should still equal 2x plus 3. But what this enables me to do is now break the fraction up in a way that's helpful, given what I'm trying to do. So 2x minus 1 over x minus 1 is just 2 plus 5 over x minus 1. Okay, haven't done any antidifferentiating, so we still have our integral sign and our dx. Now we're ready, to antidifferentiate. Antiderivative of 2 is 2x. Antiderivative of 5 on x minus 1, okay, again that's just 5 times the antiderivative of 1 on x minus 1, and the antiderivative of 1 on x minus 1 would be 1 over 1 out the front, a is 1, so we don't need to worry about that, log e of x minus 1 plus c. Once again, we've got this clarification that x is bigger than 1, which ensures that there's no problem with our log at the end here. Okay. Let's, however, think about what would happen if we don't have the domain restriction. Okay, so the problem that arises is the implied domain of this function that we're trying to integrate is r excluding 0. However, that's an issue for the answer because log e of x is not defined if x is r excluding 0. So we either need to restrict x to just be positive values before we antidifferentiate it so that that works for both, or we need to think a bit harder about it. This used to be simple when we had an extra thing in the course, and technically now whenever you see antiderivatives of logs, I'm confident that they will always give you a domain that means that you can just do what we've been doing, a restricted domain. However, I do just want to touch on what happens if we don't have the restricted domain, in particular because we see this with our CAS. Okay, so let's have a think about, as I said, there's issues with domain. So the original function 1 on x is a hyperbola. Its domain, therefore, is r excluding 0. The antiderivative is log e of x, but its domain is only r plus. And so, therefore, this rule only works if x is bigger than 0. Okay, and we're not looking at this bit back at the beginning. Let's, however, think about what would happen. So remembering what we have here is a connection between gradient function. Okay, we're anti-differentiating though. So what we're saying is this is the original function, this is the gradient function. Okay, and that should make sense. When x is very, very small positive value, we have a really big gradient. So that's where my gradient function's right up here. And as x gets bigger, my gradient always remains positive, but it gets smaller and smaller and smaller. And so that's where we get that truncus kind of shape. So let's see if we can reverse that and think about, okay, well, what would the original function have looked like to give this bit as the derivative function? It's clear that it's always got negative gradient, and it starts off with quite small negative gradient, then becomes a very big negative gradient. And so what's actually happening here is if I were to also have a log function here that's symmetric to this one, then things would make sense. Okay, so if we also had y equals log e of negative x, then it would be true that the integral of 1 on x, so the integral of 1 on x with respect to x, would be equal to log e of plus or minus x. Okay, it's only equal to positive x if we say that x has to be equal to 0. Now, this is not something that's very nice, and we have a nicer way of essentially saying the same thing, which we no longer have as part of the course. Okay, so this is what we're talking about here. So we would actually need the antiderivative of 1 on x, if we had no restriction, would be equal to log e of x when x is bigger than 0, but log e of negative x when x is less than 0. Okay, and more generally, that would be this kind of thing. It would be log e of ax plus b if we're to the right of the asymptote, which is at negative b on a, or it would be log e of a times negative x plus b if we're to the left of the asymptote. Now this can be written much more succinctly using the absolute value function. Okay, so technically speaking, and we no longer, this used to be part of this course, and so therefore this was really straightforward. Okay, but now the absolute value function isn't part of this course. The absolute value function is a very simple function that's written like this, and it's a piecewise function. that equals x when x is bigger than 0, and it equals negative x when x is less than 0. Okay, so therefore that covers in that plus or minus x, positive x when x is bigger than 0 and negative x when x is less than 0, which is what we need to happen up here. Okay, so a simpler way to write this, and we would never write this, is to use the absolute value function. So the antiderivative of 1 on x with respect to x is actually log e of the absolute value of x. And that then means that we don't need a domain restriction, because it means if x is a negative value, if you put a negative value into the absolute value, it makes it positive. Okay, so 1 on x is defined, for example, when x equals negative 3. Log e of the absolute value of x is also defined when x equals negative 3, because the absolute value of negative 3 is positive 3. Okay, so I don't want you to worry too much. You don't need to have an understanding of absolute value. So the same is true if we want to antidifferentiate 1 on ax plus b, where there's no domain restriction. In order to make sure our log is defined, we're going to need to use log e of the absolute value of ax plus b instead of just round brackets. Okay, so I would encourage you, just as a general rule, to get in the habit of just writing your antiderivatives of logs using straight lines instead of round brackets. Okay, as I said, I'm pretty confident. I haven't seen any issues in the last few years since we got rid of absolute value function out of the course. I haven't seen any issues in the exams with domain here. But it is worth noting because you see it in your CAS. So you can see here in this screenshot I've included here, if you were to antidifferentiate 1 on x with respect to x and give a domain restriction where x has to be bigger than 0, then it will tell you it's log e of x with round brackets. But if you just antidifferentiate 1 on x without bothering to put the domain restriction in, it will tell you that it's log e of absolute value of x. Now I don't want this to freak you out when you see it in your CAS, so I want you to have that understanding that the reason it's doing that is because there's no domain restriction here. I also want you to understand that you don't have to type in the domain restriction to understand that you can just write your answer with round brackets as long as there is a domain restriction in the problem. If there isn't a domain restriction in the problem, so if it doesn't say x has to be bigger than 0, then we really do need to have the absolute values. Okay, so for example here, where we're just asked to antidifferentiate 5 on x, it doesn't tell us that x has to be bigger than 0. So the implied domain here is that x could be any real number except for 0. And so therefore, when we calculate our antiderivative, which will be 5 times log e of x, we're going to need for it to be 5 times log e of the absolute value of x, so that we can accommodate the negative values in the domain, negative x values in the domain, and then plus c. So as I said, I don't want you to worry about too much about what does the absolute value function mean. Just get in the habit of writing those straight lines instead of writing the brackets when you antidifferentiate log functions. Antiderivative of 2 over 6 minus 7x with no domain restriction suggests that the domain is any real number except for, what will it be, 6 on 7? Okay, that would be where the asymptote is. And so therefore, to accommodate the values that would make the denominator negative, and hence make the log function log of a negative, we need to use the absolute value. So antiderivative of this would be, the 2 just goes out the front. We need to also divide by a, so dividing by negative 7, and then it's going to be log e of, and I'm going to use absolute value of x, of the denominator, to make sure that the fact that there isn't a domain restriction, I can still put any value of x in here. If it makes 6 minus 7x negative, the absolute value functions will then make that value positive, so it's fine to calculate log. And don't forget our plus c. As I said, I don't want you to get too bogged down in this, but I do just want to raise it because you will see it with your CAS when you antidifferentiate log functions. You're more than welcome to just always write the vertical lines, so the absolute value. If you'd prefer to stick with round brackets because you're not feeling comfortable about the absolute value, that's fine, but it would only be correct to do so if the question said that x was bigger than 0 and said there'd be no issues with that. Okay, as I said, I'm pretty confident that VCAR is making sure that that happens, but I just don't want the absolute values to freak you out when you see them on your CAS. Okay, so the work today is from exercise 11C.